Hello and welcome back to PC Retro Programmer. In this video I'm going to be talking about the purpose of CPU registers, and of course we'll be discussing the 8086 and 8088 CPUs, which are 16 bits internally. And so what this means is that they have 16-bit registers inside them that the CPU can do various operations on. Now there are a couple of different reasons why CPUs have registers, and these relate to the function of the CPU itself. So the first thing that the CPU can typically do is arithmetic operations like addition and subtraction of different values. They can also do logical operations, for example, logical AND, logical OR, logical XOR, and so on. So there's all these operations that they can perform on values. Now there's nothing particularly stopping you having a computer system that allows you to do operations directly on memory values, but there's only really two ways that you could achieve this. The first would be to have a bunch of really complicated circuitry inside the memory chips themselves to do those operations on the values that are in the memory. But this would complicate memory greatly and make it really expensive, so we don't do it that way. Instead, we have a CPU that does the operations, but that means that you have to load the values from memory into the CPU before they can be operated on. And this can be really slow because memory access is typically quite slow. For example, on the 8088 CPU, it takes 8 cycles to read a 16-bit value into the CPU from memory, and similarly to write one back. So if you have two values that you wanted to add together, you'd have to read them both in, that's 16 cycles, do your operation, then another 8 cycles to write the result back out to memory. So you certainly don't want to do that every single operation. And so the way it usually works is that the CPU offers some small internal storage locations called registers, and on the 8086 and 8088 these are 16 bits each. And you read into those registers the few values from memory that you're currently interested in, and while they're in the registers inside the CPU, you do as many operations as you can on those values in the CPU. And then when you're done, you write the result back to memory once, and so this saves a whole load of reading and writing overhead. Now the second reason why CPUs have registers has to do with memory itself. So if you do want to read from memory into the CPU or write back to memory, you need to tell the CPU where in memory. And for this purpose, memory locations are numbered. So each byte is numbered starting from 0 at the beginning of memory, and these numbers are called addresses. So the address gives the location in memory that a value is stored that you're interested in. And so it makes sense to have registers in the CPU that can hold addresses, not just values that you're going to be operating on. So that's the second reason that CPUs have registers. Now back in the 8-bit era, a lot of CPUs had 8-bit registers for values, and they only offered 8-bit operations that you could do on them, and they offered 16-bit registers for addresses. And so there was a distinction between the 8-bit and the 16-bit registers. Now in the 8086 and 8088 we don't need this distinction because the registers are all 16 bits, so they can all store addresses. In the 8-bit CPUs you wanted to address up to 64 kilobytes of memory, and so that's why they needed to have 16-bit registers for addresses, but they're only offering 8-bit operations. Now in the 8086 and 8088 there are 8 general purpose registers, and basically all of the simple operations that the CPU can do work equally well on all of these registers. So addition, subtraction, shifting and rotation, and so on. So these CPUs are very, very flexible, and as I said, you can put addresses in any of these registers. They also have 8-bit registers, but these are just halves of existing 16-bit registers. So for example, the AX register is divided into a high byte and a low byte, which are called AH and AL respectively. And so the CPU does offer 8-bit operations as well. You can just take 8-bit registers and add them together, or subtract them, or XOR them, or whatever. So in general, you don't need the distinction between registers for values and registers for addresses. But there are some assembly operations that work with memory and need an address to operate, and those tend to be a bit picky about which registers. So they tend to want to use BP, DI, SI, or BX. So we'll look at these instructions today, all the basic operations that the CPU does. In addition to that, there are some very specialized operations that the CPU does, and those tend to only work with one or a couple of registers. And so we'll look at those a little bit later. I'm not going to go into a lot of detail with those, but I'll try and give you a feel for the specific purposes that the registers have when they're used with these specialized instructions. Now in the 8-bit CPUs, they tended to also have one distinguished register called an accumulator, and a lot of operations had to be done via the accumulator, especially when working with memory. But this is not really the case in the 8086 and 8088. AX is still called an accumulator, and so is AL. That's the 8-bit accumulator and the 16-bit accumulator. But there are very, very few operations that only work with the accumulator. Most of the basic operations, as I said, will work with all of the general purpose registers, so they're very flexible. In the 8-bit CPUs, some of them allowed you to combine two 8-bit registers together, specific 8-bit registers to make a 16-bit register, but then they'd only offer very, very limited 16-bit functionality. And sometimes they allowed you to join two 8-bit registers together to make a register to store an address. But for the most part, they were much more limited, and a lot of things had to go via the accumulator. Now the 8086 and 8088 really didn't develop in a void. Intel had already developed a very successful CPU called the 8080 CPU, which was an 8-bit CPU, and there are actually links between the way that the 8080 works and the way that these two 16-bit CPUs work. So some of the registers kind of have correlates in the 8-bit CPU, and so it's actually an interesting study to figure out what it was that Intel intended all these registers to be used for. But I guess that's a story for another video. For today, I'm just going to focus on very standard 8088 and 8086 assembly language. So there are some other registers in these CPUs. There are 4 segment registers, and I won't talk about those directly today, but it turns out that the 8086 and 8088 can address up to 4 64 kilobyte blocks of memory at once. And the start addresses for those are stored in segment registers. Now these are not general purpose. They have very few operations associated with them at all. They're really just for storing segment addresses in a particular format. And so they're not useful as general purpose registers. You can, if you really know what you're doing, use them for extra storage, but this is rare. Their main purpose is segment addresses. There's also a flag register. It's a 16-bit register, but a number of the bits don't do anything, and they're either 0 or 1 permanently. They're used on later CPUs, but not in the 8086 and 8088. And the remaining bits have names. They're called flags. For example, the most recent arithmetic operation, the result of this would set the sign flag. And if it was a positive result or a negative result, that would be reflected in the sign bit of the flag register. Now there's actually one other 16-bit register, but it's not used in assembly language programs. In fact, you can't use it directly. It's the instruction pointer, And this is used by the CPU internally to keep track of where it's up to in the code that it's executing. So it contains an address, and it's the address within the code segment that it's up to at the current moment. Now, there are assembly language instructions that will modify it. Of course, if you do a jump to a different location in memory, that will change the instruction pointer, and of course if you call a subroutine, that'll change the instruction pointer. But you don't ever modify it directly. You never see IP in an assembly language program. And so that's really just hidden away from you inside the CPU. You just know that it's there and don't get to use it directly. So what I'm going to do today is fire up debug. We'll put some values in the registers, and then I'll go through all the instructions that work equally on all of these registers. And then a little bit later I'll try and give you a little bit of an overview, a little bit of a feel for what some of the specific purposes of these registers are for those very specialized instructions that only work with one or two different registers. Now, the nice thing about debug is it allows us to see what's in the registers. Everything's in hexadecimal here, but you can see all of the values that are currently in all of the registers, even the IP register. And things are not quite set up exactly the way I want here, so I'm just going to make one small change using a debug command. I'm just going to put 1942 in the DS register. The reason I'm doing that is I just want the data and the code to be separated by some distance. So the code will go in the CS segment and the data will go in the DS segment. And so I'm just separating those two apart. But now everything's set up and I'm ready to start showing you how to use this. So the debug program has a little assembler built in, so I can actually assemble code, and I'll just start at the address 0, and I can put in something like, let's do move AX 1 2 3 4. Now the values here are hexadecimal. This is not the decimal number 1 2 3 4. So I'm going to assemble that, and it'll assemble it down into machine code for me. So if I now unassemble at 0, you can see that first instruction there is now move AX 1 2 3 4, and it converted it into machine code, which is B8 3412. You can see the 1 2 and the 3 4 get switched around there. So now we can actually run that instruction, so let's do that. So P equals 0 will run this for us. It'll just proceed starting at 0 for one instruction. And so now we've run it, and you can see that AX now has the value 1 2 3 4 in it. Now this is great for moving a constant value into a register. So these constant values, we call those immediate values in assembly language. So we've moved the immediate value 1 2 3 4 into the AX register. Now, of course, the other thing that we want to do is to move stuff between registers. So let's now move that value into the BX register from the AX register. We always put the destination on the left, and we always put the register the values coming from on the right. So let's do this, and we'll run it and see what happens. And there you can see we now have 1 2 3 4 in the BX register as well. It's been copied from AX into BX. Now you can also move immediate values into an 8-bit register. So let's change the value of the AH register, the high byte of the AX register. Let's change that to FF. So let's do move into AH, FF. Everything here is in hexadecimal. And let's run that. And there you have FF now in the AH register, the top half of the AX register. We can also move stuff between 8-bit registers. So let's move that value from AH into the CL register. So let's do move into CL AH. Again, the destination is on the left. And let's run it. And you can now see that we have FF now in the CL register, the low half of the CX register. So basically we can move data about in any of the 8 general purpose registers. That's the 8 on the top line there. So I've restarted debug, and what I want to show you now is how to move data from memory into a register, or from a register into memory. And first of all, let me just show you what's actually in memory, and I'm just going to use the debug dump command for this. And the first time I do that, I have to tell it what segment I'm using, and I'm using the data segment. So dumping from address 0, this is what I get. And you can see there's a bunch of strings in there at the moment, probably from MS-DOS. And what I want to do is read some values in from memory, some of these locations here, into registers. And you can see all of the hexadecimal bytes that are in memory in the middle section there. So let's read some of those in, and the first thing I need to do is set up an address, and the way I'm going to do that is to put the address in a register. So let's use the SI register, and I'll use address 2. So we already know how to put the value 2 in SI. And so just taking a look at that middle section there, it starts off at address 0, that contains 6C, and then address 1 contains 6.1, and then address 2 contains 7.9. So if we read that byte in, which we'll do now, then we should get 7.9 read in. And the way we read in from memory is we put square brackets around the thing. So in this case, what it's saying is not that I want to read the value of the SI register into AL, wouldn't work anyway, it's a 16-bit register. But instead, I want to read the memory location whose address is in SI into the AL register. So that's what that looks like. And while we're at it, we'll also do DI. I think DI contains 0 at the moment, so that'll read from address 0. And that contains a 6C instead of a 7.9, so that'll be a bit different. And the other thing I'll do is BP. Now there are only 4 registers I could use here. I could use either of the index registers, SI or DI, or I could use either of the base registers, BX or BP. But BP works a little bit differently because instead of defaulting to the data segment like all the others, it defaults to the stack segment. And so at the moment, the stack segment and the data segment aren't in the same place in memory. I moved the data segment right at the beginning using a debug command, so it'd be in a different place to all the others. And so this is actually going to read from the stack segment instead, which will probably have a different value in it. We haven't actually printed that out. Now you can actually override the segment and tell it to use DS anyway, and the normal way to do that would be this. So you just put DS colon in front of the address, and this is called a segment override. So you can use any of the segments for the override, CS, DS, ES or SS, and you can use it with any of the instructions that use addresses. Now this is not exactly what debug wants. Unfortunately, it's a very primitive assembler, and it requires the segment override to be on a previous line. It actually costs you a byte of machine code, by the way. So what it really wants is this. So that segment override only affects the next instruction, so just that one move ALBP. Alright, the other thing that we can do is to move 16 bits from memory, and so I'll use address 0, which is in the DI register, and I'll move 16 bits from there into AX. And you can see in the middle section there where I did the dump, the 16 bits are going to be the value 6C61. So that'll read those in. So let's run this and see what happens. The first thing it's going to do is the first instruction there, which is to move 2 into SI. We've already seen that before. So there we have 2 in SI. So that's our address set up. And here's where we actually read from memory. So it's reading the value at address 2, And it even tells us helpfully in the bottom right hand corner there what the value is that it's going to read in. It says in the data segment at address 2 the value is 79. So let's check, and yep, it puts 79 in the AL register. So now we're going to read from address 0, because DI contains 0, and it tells us that it's going to read a 6C, and it does. And here's where it's different. BP, remember, is with respect to the stack segment, and Debug's figured this out. It's actually showing SS instead of DS now, and apparently at address 0 in the stack segment we have the value BE. So let's read that in, and that's working. So now we have the version with the segment override. So it's now figured out again that we're going to be using the data segment again, and so we're just back to our normal 6C. So now we'll read in a word, so we're using the 16-bit register AX instead, and so this is going to apparently read in 616C. But let's actually have a look at what's happened here. So in memory at address 0, the word that's there is 6C followed by 61. Those are the 2 bytes. But in the AX register we have 616C, so it seems like it switched them somehow. But actually nothing's been switched. The low address here is address 0, and that contains 6C, and that's gone into the low byte of AX. And the high address is address 1, and that contains 61, and that's gone into the high byte of AX. So nothing's been switched, it's just the funny way that we write numbers. So that is how you read a word from memory. Now let's go the other way around and write from a register into memory. So it's exactly what you think it is, you just swap the order of the operands. The destination is always on the left. So let's first of all move into address 2, which is what's in SI, the value in AH. And then let's move a word in to address 2. So in fact let's move SI in. There's nothing stopping us doing that. And the other thing that you can do is to move constants in, immediate values. So let's try that. So let's see what the assembler does with this. Well, it complains, and the reason is it doesn't know whether there's a byte to be moved in or a word to be moved in. It can't tell from the value itself, and it certainly can't tell from the address. The address could be the address of a word or the address of a byte. So what you have to do is tell it, and the standard way is to write byte PTR, which stands for byte pointer, to tell it that DI contains the address pointing to a byte rather than a word. And then we could move 12 in. So that now works. And the other way is with word PTR, and this will move a word into that address. So let's put the word 123 in this time. So let's run these and see what happens. So the first thing it's going to do is move AH into address 2, and AH contains 61 at the moment. So let's dump and see what happened. And now you can see 61 is in location 2. So now let's move SI in. So that's going to move a 2, but the word 2 into address 2. And again, it looks like things are back to front, but yeah, it's moved it into location 2. And so now let's move a byte into address 0. So DI contains 0, and the byte is going to be 12. So let's take a look. And yep, let's put 12 in. And now we'll put the word 123 into address 0. And again, it looks like it's back to front, but it has put the right thing in. So there are a couple of other things that you can do with the move instruction. The first is that you can move between a general purpose register and a segment register, and vice versa. But that's basically all I'm going to say about the segment registers, because that's pretty much all you can do with them, other than the segment overrides that I talked about. You have to use some fairly specialized instructions to make use of them in other ways. But segments themselves are quite complicated, and I'm going to do an entire video on that. So I won't say any more about those. But basically none of the other instructions that I talk about today are going to apply to segment registers. So the other thing I want to show you is another interesting thing that you can do with moving. So we'll still be moving into memory, but what we're going to do is specify the address directly. So let's move, let's say SP into that address. And I'll also move AX into that address. And there's going to be a difference between these, which you'll see in a moment. And similarly, we'll move AH into the address. And then we'll move AL. So those are bytes that I'm moving in. Okay, now the difference is when I unassemble these. So let's unassemble 0 and see what it has come up with. So it's a little bit weird. The first two are both 16-bit moves because SP and AX are both 16-bit registers. But the first one assembled down into 4 bytes of machine code, and the second one assembled down into 3 bytes of machine code. So what gives? Well, the answer is that this particular instruction has an optimization if you use the accumulator. So either the 8-bit or the 16-bit accumulator. So that second one, AX, is being moved in. That's the 16-bit accumulator. And so you actually save a byte of machine code with this one. Very bizarre, but this is one of the things that Intel wanted to do. And again, if I move AH in, that's just considered a general register, and so that's 4 bytes. But if I move AL in, that's the 8-bit accumulator, and that's optimized. So that goes in 3 bytes. So this is quite a saving sometimes. Now, this is something to bear in mind in an assembly language program, but you might not recognize this sort of code from an assembly language program, and that's because you don't normally work with direct addresses in assembly language programs where you have a constant address, or at least you don't know that you're working with them. Normally in an assembly language program you use labels. So you'll have some location perhaps in your data segment, and it'll have a name, a label, and you'll use that instead, and the assembler and the linker and DOS will actually convert these into actual constant addresses. So whenever you are moving the accumulator into memory, or actually from memory, then you get a saving of 1 byte. So look out for that whenever you're using labels that are going to translate down to a direct address like this.